There's a moon circling Saturn that refuses to play by the rules. When you first see it, something feels wrong. Not immediately obvious, not screaming at you, but wrong in a way that nags at the back of your mind. It's not the color, it's not the rotation, it's something else entirely. A feature that shouldn't be there, a wall. An enormous wall running across the equator, like someone took a ruler to the surface and decided to build a mountain range along that single line. And here's what makes it truly unsettling. Everything we know about how moons form, how they evolve, how they behave over billions of years, tells us that this structure cannot exist. Not like this. Not in this configuration. Not with this precision. Yet there it stands, defying our models, challenging our assumptions, forcing us to reconsider what we thought we understood about planetary formation itself. Before we dive into competing theories, before we examine the data or the calculations, we need to confront the fundamental question that drives this entire mystery. How does a celestial body, this small, this cold, this geologically inactive, end up with a feature this massive and this geometrically perfect? And why, of all places, does it sit exactly where it does? Right on the equator. Not close to it, not approximately aligned with it, on it. As if someone drew a line around the moon's middle and then raised that line 20 kilometers into space. This is where our story truly begins. The first thing you need to understand about this wall is what it actually is when you strip away the comparisons and the metaphors. We're talking about a ridge that extends along most of the equatorial circumference, broken only by scattered gaps. Some sections rise nearly 20 kilometers above the surrounding terrain. Think about that number for a moment. 20 kilometers. That's more than twice the height of Mount Everest. But we're not talking about Earth. We're talking about Iapetus, a moon with a diameter of only 1,470 kilometers, roughly one-third the size of our own moon. Yet this tiny world hosts topography that, when you account for its gravity, which is roughly 1/4 of Earth's, becomes proportionally more extreme than almost anything else we've observed in the inner solar system. On a body this small, that height becomes absurd. If you could transplant a mountain like this to Earth, it would dominate entire continents. But on a moon where gravity barely holds things down and where the crust consists primarily of water ice, such a structure shouldn't remain stable over geological timescales. The ice should flow, deform, collapse under its own weight. Yet there it stands, unchanged, ancient, immovable. The ridge doesn't meander across the surface like a normal mountain chain. It doesn't curve with the terrain or follow any visible geological weakness. It traces the equator with such precision that when scientists first analyzed the Cassini imagery, they thought there might be an error in the data. Natural mountain belts don't form in perfectly straight global lines. They bend, they twist, they respond to the chaotic forces that create them. Even Earth's longest mountain chains, the Andes stretching along South America, the Rockies cutting through North America, follow the collision zones of tectonic plates. They curve because the plates themselves curve. They shift direction because the forces driving them are complex and multi-directional. But this ridge on Iapetus shows almost no deviation from the equatorial line. It locks onto that circle as if guided by something far more precise than random geological processes. When you examine the ridge's shape in detail, the mystery deepens. Many of the peaks display clean triangular profiles, steep sides rising at consistent angles, sharp crests where those sides meet. This is the geometry you see when loose material piles up under its own weight, when debris accumulates at a natural angle of repose. It's not the shape you get from tectonic forces pushing crust upward from below. Tectonic uplift creates fractured blocks, folded layers, complex stress patterns. This ridge looks different. It looks built, not pushed. The base width varies from 20 to 70 kilometers. The slopes maintain steep but consistent angles. The cross-section remains remarkably uniform across vast distances. All of these characteristics suggest that material was deposited along the equator rather than forced upward through it. Something piled debris along this line. Something kept piling it for a very long time. And then there's the surface condition. The ridge is heavily cratered, absolutely covered in impact scars. This tells us immediately that we're looking at something ancient. Whatever process created this feature happened early in the moon's history. Crater density measurements, which scientists use to estimate surface age, show no indication that this is a recent formation. The impact count suggests the ridge is nearly as old as the surrounding plains. In some areas, it might be just as old. This age creates another profound problem. If the ridge formed through internal processes, through volcanic activity or tectonic deformation, you need a warm interior. You need heat to drive those processes. You need a partially molten layer that can move, that can push material around, that can reshape the crust. But if the ridge formed very early, during the moon's youth, and the interior cooled rapidly as small icy bodies tend to do, then the window for such activity would have been extremely narrow. The heat would have dissipated quickly. The interior would have frozen solid. After that, no internal force could build something this massive. The ancient age also constrains the possible mechanisms dramatically. A younger ridge could potentially be explained by later thermal events, by delayed tectonic adjustment, by some unusual crustal stress that developed over time. But an ancient ridge means whatever created it happened during the formative period. It had to occur while the moon was still establishing its fundamental characteristics. It had to be fast. It had to be powerful. It had to affect the entire equatorial region simultaneously. That's simply not how small, icy moons typically behave. They don't suddenly develop enormous equatorial mountain ranges while they're cooling down from formation. They don't concentrate geological activity along one perfectly defined line. They don't build structures that remain geometrically pristine for billions of years. So you're left staring at a feature that is massive, perfectly aligned, sharply defined, and extraordinarily old. Every single attribute contradicts what we expect from natural processes operating on small frozen worlds. Every measurement, every observation, every analysis pushes the ridge further outside the boundaries of normal planetary geology. And this is precisely why, 2 decades after Cassini first revealed it in high resolution, the ridge remains one of the most baffling features in the entire solar system. Not just unusual, not just unexpected, genuinely inexplicable using conventional frameworks. Iapetus orbits Saturn at an average distance of 3.56 million kilometers. That places it far beyond the bright ring system, out in the colder, darker reaches of Saturn's gravitational domain. The moon sits roughly 9.5 astronomical units from the Sunday. That's about 1.4 billion kilometers from Earth at typical opposition. Because of this enormous distance and the moon's relatively small size, surface features remained completely mysterious for centuries. Even powerful Earth-based telescopes could barely resolve the disk, let alone detect mountains or ridges. Everything changed when the Cassini spacecraft arrived at Saturn in 2004. During a single close flyby in September 2007, Cassini swept past Iapetus at a distance of just over 1,600 kilometers. The images it returned were stunning. They revealed the ridge in extraordinary detail. They showed its height, its extent, its precision. They gave planetary scientists their first real look at what one researcher called a tough nut to crack, and another described as one of the most astonishing features we've ever seen anywhere in the solar system. But before we can really talk about theories for the ridge, we need to understand the world it sits on. Because Iapetus itself is strange, profoundly strange, in a way that makes the ridge even harder to explain. One hemisphere of Iapetus is extremely dark. It absorbs most of the sunlight that strikes it, reflecting back only a small fraction. The other hemisphere is bright, covered in relatively clean water ice that reflects light efficiently. This isn't a subtle difference. This isn't a slight variation in albedo that you might notice if you looked carefully. This is a dramatic, hemisphere-spanning division that makes the moon look like someone dipped one entire half in coal dust and left the other half pristine. The dark region is called Cassini Regio, named after the astronomer who first noticed the moon's unusual brightness variations in the 1600s. The material coating this region appears to come from outside the moon itself. The current best explanation involves a slow accumulation process. Dust from Saturn's outer moons, debris from retrograde irregular satellites, material knocked loose by impacts throughout the system. All of this gradually builds up on Iapetus's leading hemisphere. As the moon moves through its orbit, it sweeps through this tenuous cloud of particles. The dark material settles preferentially on the side that faces forward. Once that dark layer forms, it creates a feedback loop. The dark surface absorbs more sunlight. It heats up more than the bright regions. That warmth causes the ice beneath the dark material to sublimate, to turn directly from solid to vapor. The water vapor migrates toward the colder, brighter hemisphere where it refreezes. This process makes the bright side even brighter and the dark side even darker. Over millions of years, the contrast intensifies until you get the striking two-tone pattern we see today. Now here's where it gets interesting for the ridge. The ridge sits almost entirely within the dark hemisphere. It's not centered between the two regions. It doesn't transition smoothly from bright to dark terrain. Instead, the ridge is strongly associated with Cassini ratio. Most of it runs through the darkest areas. That placement adds enormous pressure to every model attempting to explain the ridge's origin. If the ridge came from internal forces, why would it preferentially develop in the dark hemisphere? Why wouldn't it be evenly distributed around the entire equatorial band? Internal processes don't care about surface color. They don't respond to albedo variations. Volcanic activity, tectonic stress, convective upwelling, none of these mechanisms would target the dark side specifically. On the other hand, if the ridge came from external material falling onto the surface, why would that material land predominantly on the darker half? Orbiting debris doesn't selectively target one hemisphere based on surface brightness. The color division also affects the thermal evolution and mechanical properties of the crust. Warmer regions behave differently over geological time. Ice that experiences regular heating cycles can slowly deform, can flow like an extremely viscous fluid, can gradually slump and settle under its own weight. The ridge stands in a region where surface temperatures are higher than average, where thermal cycling is more pronounced, where you'd expect more long-term modification of surface features. Yet the ridge remains sharply defined. It hasn't noticeably slumped. It hasn't spread out into a broad, rounded swell. A feature 20 kilometers tall, standing on a relatively warm, icy surface, should show more signs of gravitational collapse, especially over billions of years. The fact that it doesn't suggests either that the ridge is composed of unusually strong material or that it formed under conditions that somehow locked it into place early on. The two-tone pattern means that any complete explanation for the ridge must account for both the structure itself and the surface chemistry. You can't treat them as independent mysteries. The dark material fundamentally changed how the moon evolved thermally. It altered the surface temperature distribution. It modified the sublimation and deposition patterns. The ridge sits directly in the middle of that altered environment. It's unclear whether the ridge formed before the dark coating settled or whether the coating arrived after the ridge already existed. Both scenarios create challenges. If the ridge formed first, why did the external dust coating follow the equator so precisely? Why would it preferentially coat a pre-existing elevated feature? If the coating came first, why would a subsequent geological process build a ridge exactly where the thermal conditions are most unusual? Instead of clarifying things, the hemisphere dichotomy adds another layer of complexity. It ties the ridge to a portion of the moon that behaves differently from the rest, and that connection makes every theory more difficult to test, more difficult to verify, more difficult to accept. The ridge isn't just an isolated anomaly sitting on an otherwise normal moon. It occupies a region that has been shaped by external dust, by thermal migration, by long-term ice movement. That context matters. It means the ridge exists within an environment that was already being modified by unusual processes. Whether those processes contributed to the ridge's formation or merely coincided with it remains one of the central questions driving ongoing research. When planetary scientists first saw detailed images of the ridge, the natural instinct was to fit it into familiar geological categories. Icy moons aren't geologically dead. They shift, they crack, they fold and reshape themselves under various internal forces. Some develop long troughs when their crusts expand or contract. Others display complex fracture patterns from tidal stress. Scientists have documented numerous examples of tectonism on icy satellites throughout the solar system. But none of those processes line up cleanly with what we observe on Iapetus. Tectonic activity typically creates features that stretch across a surface in irregular, sometimes chaotic paths. These features might follow patterns determined by interior heat distribution, by crustal thickness variations, by zones of mechanical weakness, but they don't trace planetary coordinates with surveyor-level precision. Tectonic ridges don't appear as single sharp structures running continuously around an entire world. They segment. They shift direction. They interact with other fault systems. They respond to the complex stress fields that create them. On Iapetus, the ridge stays locked to one line. It shows no signs of drifting away from the equatorial path. no significant deviations, no major directional changes. That kind of precision immediately makes a purely tectonic origin highly unlikely. William McKinnon, a planetary scientist at Washington University in St. Louis who has studied Iapetus extensively, has pointed out that some researchers initially proposed the ridge might have been caused by a chain of volcanic eruptions or perhaps by a system of parallel faults. But to align everything so perfectly along the equator, he notes, there's simply no comparable example anywhere else in the solar system. We have no precedent for that kind of geological organization on a small, icy moon. Volcanism doesn't help explain it either. Ice volcanism, or cryovolcanism, as it's technically called, produces very different morphology than what we see in the ridge. When water or ammonia-rich slurries erupt onto the surface of an icy moon, they create rounded domes. They form smooth flow fields. They produce broad plains of erupted material that spread out from central vents. They don't create narrow walls stretching for more than 1,000 kilometers. They don't build steep-sided peaks with sharp crests. There are no visible vents near the ridge, no channels, no flow patterns, no evidence of different eruption stages, no overlapping sheets of frozen material that would indicate multiple eruption events. The structure rises too steeply, too cleanly, too uniformly for volcanic construction. If this were an eruptive feature, the evidence would be unmistakable, but the ridge shows none of the characteristic signatures. Internal convection represents another possibility that initially seemed plausible. Small, icy moons can experience slow churning motions in their interiors. If enough heat remains to keep deeper layers soft, this convection can push overlying crust upward, forming long belts of elevated terrain. We've seen evidence for this kind of process on several moons. But convection-driven features don't run exclusively along the equator. They don't maintain constant width and height across nearly an entire hemisphere. They tend to form broader, smoother uplifts, rather than narrow, steep-sided peaks. A convective process powerful enough to lift ice to 20-kilometer heights would almost certainly create global deformation. You'd expect to see fractures elsewhere, compensating depressions, signs of crustal adjustment across the entire surface. Those global indicators don't exist on Iapetus. Computer simulations of plume-driven resurfacing on icy satellites predict chaotic upwelling patterns. They show polygonal surface textures similar to what we observe on Ganymede. They produce variable relief that tapers unevenly across the affected region. They create associated zones of disrupted terrain surrounding the main uplifts. The Iapetus Ridge displays none of these characteristics. Its elevations remain uniform. Its structure stays narrow and well-defined. It lacks the surrounding chaos that convective processes typically generate. Another idea that initially attracted some attention was global contraction. When a moon cools after formation, its interior shrinks slightly. That shrinkage compresses the outer shell, creating ridges or folded terrain in places where the crust buckles under compression. We've observed this process on Mercury, on Mars, on Earth's moon. It's a well-documented phenomenon. But contraction typically produces widespread patterns scattered across the entire surface, not a single structure confined to the equator. Contractional features form wherever the crust is weakest or wherever stress happens to concentrate. They don't selectively target one latitude, and contraction doesn't explain the extraordinary height of the ridge. A compressional force running around the circumference of the moon wouldn't stack material into a 20-kilometer wall. You'd expect low ridges, broken fold systems, scattered zones of elevated terrain. Instead, the ridge is tall, narrow, and remarkably continuous. What ties all these failures together is a straightforward observation. Natural internal processes operating on icy moons do not select specific latitudes with such geometric precision. They also don't produce tall, sharp, uniformly structured peaks that remain essentially unchanged for billions of years, without similar features appearing elsewhere on the same body. Any viable model must simultaneously explain three critical observations. First, why the feature sits precisely on the equator with almost no deviation. Second, why it is confined exclusively to the equator rather than appearing at other latitudes as well. Third, why only Iapetus possesses such a ridge while other icy moons, including those with similar histories of tidal heating and impact bombardment, show nothing comparable. The ridge behaves like something constructed by a mechanism that specifically targeted one line on the moon and deposited or shaped material consistently along that path over an extended period. The complete absence of matching geological signatures leaves a conceptual gap. The ridge doesn't fit comfortably into the standard framework we use to describe how icy moons evolve. Once you've ruled out the familiar internal processes, you're forced to consider explanations involving early formation conditions, external influences, or rare combinations of events that seldom occur in planetary systems. You have to think outside the normal boundaries of planetary geology. And that's exactly where researchers began to look. Once internal mechanisms began failing to provide satisfactory explanations, attention gradually shifted toward a fundamentally different approach. What if the ridge didn't originate from inside the moon at all? What if it came from outside? The idea that Iapetus might once have possessed a ring system sounds unusual at first. We're accustomed to thinking of rings as features belonging to giant planets. But small moons can temporarily capture debris under the right circumstances. If Iapetus experienced a major impact event early in its history, an impact violent enough to excavate large quantities of material and throw it into orbit, some of that debris could have spread into a temporary disk surrounding the moon. The physics of this process are well understood. When debris orbits close to any celestial body, it experiences tidal forces. If the debris ventures inside what's called the Roche limit, the gravitational gradient across the orbiting material becomes strong enough to prevent it from coalescing into a solid object. Instead, the material remains dispersed, forming a ring. For Iapetus, anything orbiting within about 3,600 kilometers of the surface would have been subject to these tidal forces. Material in that zone would naturally spread into a thin disk aligned with the moon's equatorial plane. And here's the crucial part. That ring wouldn't last indefinitely. Rings around small bodies gradually decay. Particles collide with each other, losing energy in the process. As orbital energy decreases, the debris slowly spirals inward. Eventually, it falls back to the surface. When it falls, it doesn't scatter randomly across the moon. It descends along the orbital plane. It impacts the surface along the equator where its orbital path intersects the moon's surface. The ridge's perfectly continuous equatorial line matches this scenario remarkably well. All you need is a mechanism that drops material along one latitude for an extended period. That's exactly what a decaying ring system would do. McKinnon has described the process in vivid terms. Imagine particles coming down horizontally across the equatorial surface at roughly 400 meters per second, about the speed of a high-velocity rifle bullet, one after another, like frozen baseballs raining down continuously onto the same narrow band of terrain, hour after hour, year after year, millennium after millennium. Initially, this bombardment would have created small impact craters. These impacts would have excavated grooves, scattered ejecta, created a rough, disturbed surface along the equator. But as more material continued to fall, those depressions would gradually fill. The accumulated debris would start building upward, layer upon layer, impact after impact, slowly constructing an elevated feature through sheer accumulation. The ridge behaves exactly like something built through this kind of accumulation rather than through uplift. The distinction matters enormously. Uplift from below creates specific structural signatures. You get fractured bedrock. You see tilted layers. You observe compression features, where the rising material pushes against surrounding terrain. The Iapetus ridge shows none of that. Instead, it displays characteristics consistent with loose or semi-consolidated material that has been deposited from above. Consider the ridge's shape. Many sections exhibit triangular cross-sections. The slopes rise at angles close to what's called the angle of repose, the natural angle at which loose granular material can stack before it becomes unstable and slides downward. When debris falls repeatedly in the same location, it naturally piles up to this limiting angle. The ridge's slopes match that limit closely across vast stretches. This isn't what you get from solid crust being pushed upward by internal forces. Uplifted crust breaks. It fractures along pre-existing weaknesses. It develops complex fault patterns. It tilts coherent blocks of layered material. The ridge shows none of these signatures. Instead, it looks like something formed by steady deposition over extended timescales. The Cassini images reveal another telling detail. Numerous sections of the ridge display what appear to be landslide deposits, long streaks extending down the flanks, material that has clearly slumped downward under gravity. leaving characteristic flow patterns on the steep slopes. This is precisely what you'd expect if the ridge consisted of a massive pile of accumulated debris perched on steep inclines. Landslides make perfect sense when you have loose or weakly consolidated materials sitting at high angles. They don't make sense if you're looking at solid tectonic uplift frozen into a rigid structure. An uplifted block would fracture when stressed. A debris pile gradually shifts, slumps, and settles over billions of years. The ridge's behavior aligns much more closely with the second scenario. Another major strength of the ring collapse hypothesis lies in its natural explanation for the equatorial alignment. Material falling from orbit doesn't randomly select latitudes. It can't. Physics prevents it. Orbiting debris follows specific trajectories determined by angular momentum and gravitational forces. The lowest energy configuration for orbiting material places it directly above the rotational bulge of the central body. That bulge sits at the equator. As planetary scientist Andrew Dombard has explained, when you have debris in a ring around any body, collisional interactions between particles gradually steal orbital energy. The lowest energy state available to that material is a circular orbit right over the equator. That's why the major ring systems in our solar system, around Jupiter, Saturn, Uranus, and Neptune, all lie precisely in their planet's equatorial planes. The physics naturally drives orbiting material toward that configuration. If Iapetus once hosted a debris ring aligned with its equatorial plane, and that ring gradually decayed through collisional damping and orbital drag, the material would have settled straight down onto the equator itself. That solves one of the biggest problems facing internal models. No geological process naturally selects the equator as a target for mountain building. Orbiting debris has no choice. It goes where physics directs it. The question of origin remains, of course. Where did this hypothetical ring come from? The most plausible source is a major impact early in Iapetus's history. An impact violent enough to excavate substantial quantities of material and throw it into orbit above the surface. Large impacts can easily achieve this. We've observed impact-generated debris clouds around asteroids. We've seen evidence for similar events throughout the solar system's early history. After such an impact, the ejected debris would initially follow ballistic trajectories. Some material would escape entirely, some would crash back immediately, but a significant fraction could end up in temporary orbits around the Moon. Over time, that orbiting material would spread out through collisions and gravitational interactions, eventually forming a relatively uniform ring structure. Then the slow rain would begin. Particles gradually losing orbital energy, spiraling inward, impacting the equatorial surface, building the ridge grain by grain, particle by particle, impact by impact. This timeline matches the ridge's great age perfectly. Crater counts indicate the ridge formed early in the Moon's history. An impact-generated ring would have decayed relatively quickly on astronomical timescales, perhaps within a few tens of millions of years. That would place the ridge's formation in the period when Iapetus was still young, still actively evolving, still experiencing frequent impacts that created the heavily cratered surface we see today. The ring collapse model doesn't answer every question about the ridge. Significant uncertainties remain, but it succeeds where internal geological models consistently fail. It naturally explains the ridge's narrow width, its sharp peaks, its continuous path, and its perfect equatorial alignment. It accounts for the slope angles. It explains the signs of long-term material movement on the flanks. It transforms the ridge from an impossible geological puzzle into something that emerges naturally when orbiting debris loses energy and falls back onto a surface. The simplicity of the underlying physics makes the model particularly compelling. You don't need exotic conditions. You don't need unusual material properties. You just need an early impact, a temporary ring, and time. But some scientists eventually realized that even the ring collapse idea, elegant as it is, might not fully explain every aspect of the ridge. That realization led to a more sophisticated model, one that incorporates additional elements to address remaining puzzles. This enhanced scenario begins with the same giant impact that creates a debris disk, but it adds a crucial additional component, a temporary subsatellite. A small companion moon formed from the ejected material. This isn't as exotic as it sounds. When large quantities of material go into orbit around a moon, that material can gravitationally aggregate. Particles collide, stick together, gradually accumulating into larger bodies. Given enough time and enough material, you can form a small satellite. It wouldn't be large, perhaps a few dozen kilometers across, maybe less, but large enough to have significant gravitational effects on the surrounding debris field. This subsatellite wouldn't remain in orbit forever. Tidal interactions between the subsatellite and Iapetus would cause the small companion's orbit to gradually evolve. Over time, it would spiral either inward toward Iapetus or outward away from it, depending on the specific orbital configuration and the tidal forces involved. As the subsatellite moved, its gravity would influence the inner ring of debris. It would help spread material around the ring more evenly. It would drive inner particles inward toward the surface through gravitational perturbations. That steady infall of debris, regulated and distributed by the subsatellite's gravitational influence, would build the ridge in a more controlled, more uniform manner than simple ring decay alone. The presence of a subsatellite adds something the simpler ring model cannot easily provide: a natural explanation for Iapetus's unusually slow rotation. Observations of the moon's shape indicate it once rotated much faster than it does today. The equatorial bulge is far more pronounced than the current rotation rate would produce. That means the moon's spin has been significantly slowed over time. Tidal interactions with Saturn alone would slow Iapetus's rotation, but that process takes an extremely long time for a moon this distant from its parent planet. A temporary companion moon, however, would dramatically accelerate the spin down. Gravitational interactions between Iapetus and a close-orbiting subsatellite would transfer angular momentum much more efficiently than distant tidal forces from Saturn. The system would lose rotational energy relatively quickly. This helps explain Iapetus's puzzling shape. The moon appears to have been frozen into a configuration consistent with much faster rotation than it currently exhibits. If a subsatellite existed for a significant period during the moon's early history, it could have removed enough rotational energy to account for this discrepancy. The shape we see today would represent a snapshot of the moon's configuration at the time when it solidified and stopped responding to changes in rotation rate. The subsatellite model also helps explain the ridge's remarkable consistency. A ring influenced by a migrating companion moon would likely deposit material more steadily and evenly over time. The subsatellite's gravity would help regulate the flow of debris to the surface, preventing large fluctuations in deposition rate. That could produce the nearly continuous, uniformly structured ridge we observe today. The triangular profiles of many ridge peaks fit naturally into this framework. Repeated deposition of material onto previous layers would create exactly this kind of geometry. Each new layer settles at the angle of repose. Over time, the accumulated pile develops steep sides that meet at sharp crests. The structure builds upward as long as material continues falling. One crucial piece of evidence supports the subsatellite scenario specifically for Iapetus. Among Saturn's major moons, Iapetus possesses an unusually large hill sphere. The hill sphere defines the region around a moon where its gravity dominates over the planet's gravity. It determines how far from the moon a satellite can orbit without being pulled away by Saturn's much stronger gravitational field. Iapetus's hill sphere is large enough to have stably hosted a subsatellite for the time period required for this model to work. The small companion could have orbited for tens of millions of years, gradually migrating inward through tidal evolution, influencing the ring debris, helping to build the ridge, and removing rotational energy from the system. No other major Saturnian moon has a hill sphere this large. That might explain why no other moon in the system displays a similar equatorial ridge. Only Iapetus had the orbital geometry necessary to capture and retain a subsatellite long enough for this particular sequence of events to unfold. The timing aspects of this scenario also work well. A giant impact during the solar system's early chaotic period is entirely plausible. Most large bodies experience major collisions during the first few 100 million years. The formation of a temporary subsatellite from impact debris follows naturally from gravitational aggregation processes we understand well. The eventual loss of that companion, either through infall to the primary moon or through escape from the system, fits with what we know about orbital evolution in satellite systems. The subsatellite wouldn't still exist today. It would have been lost billions of years ago. Either it crashed into Iapetus, perhaps contributing additional material to the ridge in its final moments, or it gradually migrated outward until Saturn's gravity pulled it away entirely. The current absence of such a companion doesn't contradict the model. In fact, the model predicts exactly this outcome. Uncertainties remain, of course. The precise behavior of ring debris under long-term tidal influence from both the primary moon and a migrating subsatellite involves complex gravitational dynamics that are difficult to simulate in complete detail. Researchers acknowledge that while supporting calculations exist and the basic physics works, fully rigorous end-to-end dynamical simulations of the entire process still represent a goal for future work. The exact deposition pattern isn't perfectly constrained either. Did material fall continuously at a steady rate? Did it come down in episodic bursts when the ring became gravitationally unstable? The ridge's structure suggests a relatively long accumulation period, but not enough fine detail survives to definitively determine whether deposition was uniform or variable. And fundamentally, this model relies on early conditions that cannot be directly observed. We're reconstructing events that occurred over 4 billion years ago. We're inferring past configurations from present-day evidence. That always introduces unavoidable uncertainty. But even with these limitations, the giant impact plus subsatellite scenario stands as one of the most comprehensive explanations available. It provides a clear source for the material. It offers a specific mechanism to deposit that material along the equator. It explains the moon's anomalous rotation state during the same time period. It accounts for why only Iapetus displays this feature. No purely internal geological model offers that combination of explanatory power, which is why, since the early 2000s, this family of impact-generated ring collapse models has become the leading framework among planetary scientists for understanding both the ridge and Iapetus's extreme equatorial bulge. The evidence doesn't prove the model beyond all doubt. Science rarely works that way. But it strongly supports this general picture, while effectively ruling out most alternatives. The ridge isn't merely a bizarre feature decorating an otherwise ordinary moon. It fundamentally changes how we understand the entire object. Most moons that appear relatively smooth and rounded exist in what planetary scientists call hydrostatic equilibrium. Their shape naturally settles into a balanced configuration determined by rotation rate and internal structure. Gravity pulls everything toward the center. Rotation creates a slight outward bulge at the equator. The balance between these forces produces the moon's final shape. Iapetus doesn't follow this pattern. Its equator is significantly wider than current rotation would predict. Its poles are noticeably flattened. The overall geometry looks as though it was locked into place when the moon existed in a very different state from what we observe today. The ridge adds yet another layer to this peculiar geometry. If Iapetus once spun much faster than it does now, centrifugal force would have pushed material outward at the equator, creating an exaggerated bulge. That matches the general shape we see, but the ridge sits on top of that already widened equatorial region, making it even more prominent. It acts like a raised wall running along the moon's widest latitude, further emphasizing the equatorial zone. This suggests that whatever shaped the ridge either interacted directly with the moon's early rapid rotation, or, at minimum, arrived during the period when the moon's structure was still adjusting to changing spin rates, solidifying into its final configuration. Another important clue comes from how precisely the ridge aligns with the overall geometry. The moon's equator isn't just an arbitrary line drawn across the surface. It's a structural boundary that reflects the moon's rotational history. For the ridge to sit exactly on that boundary, its formation mechanism had to be intrinsically tied to the moon's rotation. Internal tectonic processes rarely lock onto such precise global reference frames. Faults and ridges created by internal stress typically follow paths determined by crustal weaknesses, interior heat patterns, or local geological conditions. They don't preferentially target coordinate lines defined by rotation. But orbiting debris naturally follows the equatorial plane. It can't do otherwise. The ridge's placement directly connects a surface structure to the deeper story of how the moon evolved. It links surface morphology to rotational dynamics to thermal history. All of these elements become intertwined. The combination of an exaggerated equatorial bulge, flattened poles, and a sharp equatorial ridge points toward a past where the moon's shape was determined early and then preserved for billions of years. That preservation requires rapid cooling. The moon's outer layers had to stiffen quickly, becoming rigid enough to maintain the structure before later processes could erase or substantially modify it. This makes the ridge far more than just a surface feature. It becomes a record, a fossilized snapshot of the moon's earliest physical state. The structure we see today preserves information about conditions that existed when the solar system was still young. when Iapetus was still hot enough to respond to gravitational and rotational forces, but already beginning to freeze into its final form. The ridge's remarkable stability over billions of years also tells us something important. Despite constant bombardment by micrometeorites, despite temperature fluctuations as the moon orbits Saturn, despite any slow creep or deformation in the icy crust, the ridge has maintained its basic structure. It still stands tall. It still follows the equator. It still displays steep slopes and sharp peaks. That endurance suggests the bulk of the ridge solidified or became mechanically locked early on. Whether through compaction of accumulated debris, through ice sintering, through burial by subsequent impacts, or through some combination of processes, the ridge became stable enough to resist significant modification over geological time. Viewing the ridge in context makes clear that it isn't simply an isolated mystery. It forms part of a broader pattern, showing that Iapetus formed in an environment where rotation, cooling rate, and external impacts all played significant, interconnected roles. The ridge reinforces the interpretation that this moon experienced an active, dynamic, and complicated early history. Many of its present characteristics were established during a relatively brief window billions of years ago. Instead of seeing Iapetus as just another small icy moon, the ridge forces us to recognize a more complex formation story, one involving high-energy events, rapidly changing conditions, and processes that left permanent marks on the moon's structure. Everything we know about the ridge comes from one close flyby. Cassini passed Iapetus at high speed in September 2007, gathering data during a brief window of opportunity. That single encounter produced enough information to occupy planetary scientists for decades, but it also left enormous gaps in our understanding. Many portions of the ridge were imaged at relatively low resolution. The fine details of valleys, the precise geometry of individual peaks, the small-scale textures on the slopes, all remain poorly characterized. A future spacecraft equipped with modern high-resolution cameras could fill these gaps in a matter of hours. One of the most significant missing pieces concerns the moon's interior structure. We still don't know how thick the crust is. We don't know whether there are distinct compositional layers beneath the surface. We don't know how rigid the interior became or how quickly that rigidity developed. A spacecraft carrying instruments capable of measuring gravity field variations or using radar to probe subsurface structure could reveal whether the ridge sits atop buried features or whether it truly consists entirely of surface material. Right now, those details remain hidden. Future missions could also perform direct sampling of ridge material. If the ridge was constructed from falling debris, the material along its slopes might display chemical or textural signatures distinct from the surrounding terrain. A lander or an orbiter with advanced spectrometers could detect whether the ridge consists of loosely mixed particles, uniform ice, or some combination of materials. Even subtle differences in grain size, crystalline structure, or trace composition would help discriminate between competing formation models. High-resolution mapping would clarify why the ridge varies along its length. Some sections stand tall and sharply defined. Others fade into lower, broader uplifts. Still, others appear broken or discontinuous. With detailed imaging, scientists could analyze these transitions and determine whether they resulted from variations in debris flux, changes in the early ring structure, or subsequent erosion and modification. The patterns preserved along the ridge likely contain information about the sequence of events that created it. A dedicated mission could also resolve the connection between the ridge and the dark hemisphere coating. The material that makes Cassini Regio dark still raises fundamental timing questions. If a future spacecraft measured the thickness of that coating around the ridge, analyzed how its chemistry varies with location, and studied its relationship to underlying topography, we might finally determine whether the ridge formed before or after the two-tone surface pattern developed. That single piece of information would eliminate entire categories of theories. Long-term monitoring represents another valuable goal. Small changes in surface temperature, minor movements along slopes, subtle shifts in material distribution could reveal whether the ridge remains dynamically active on human timescales or whether it has been completely frozen for billions of years. Even slight variations would provide insight into the ridge's current mechanical state and long-term stability. Until another spacecraft visits Iapetus, the ridge will remain partially understood. Cassini gave us a glimpse, a tantalizing first look, but far from a complete picture. The data we have is sufficient to rule out simple explanations and to identify the most promising models. But it's not sufficient to definitively solve the mystery. A future mission could transform our understanding. It could show us precisely how this moon ended up with a feature that continues to challenge our expectations about how small icy worlds evolve. It could reveal whether our current leading theories are correct, or whether we're still missing something fundamental about this extraordinary structure. The ridge stands there, circling Iapetus's equator, waiting for us to return and finally understand it completely.